All right. At this point, this is usually where I stopped in one day. But we're going to continue on. Concept 3, placing of shapes in a coordinate plane. At some point, we're going to try and prove something that's going to deal with the length formula, midpoint, or slope. And when we do this, we generally back off from the 2-column or the flow proof, and we show our work, and when we write a conclusion based on what we see. But before that, what we usually do is we place a shape into a coordinate plane. And it needs to be arbitrary, and that word means it has to be generic. It can't be one specific triangle. It has to be for any triangle of that type. So if it's isosceles, I can't just lock it in to have lengths of 4. It could be any leg length. When I put it into a coordinate plane, though, I want it to be convenient. I want the coordinates to have as many zeros as possible for any of the coordinates, and I want to avoid using fractions in a proof if at all possible, and I want to use variables instead of numbers for the coordinates. Exception is 0. So here's an example of a convenient isosceles triangle in a coordinate plane. So right here, this is convenient because if I look here, this length, if I plugged it into the distance formula, would be the square root of a squared plus b squared. Same one with this one over here. This would be square root of a squared plus b squared. So these two lengths are equal. And this bottom length ends up being 2a. This is an isosceles triangle, and it includes every single possible isosceles triangle. And 3 of the coordinates are 0. Makes it nice and convenient for me. This over here, I could make this an isosceles triangle. However, it'll be a little bit harder. I would still probably place it horizontal, but if I'm doing something like this, this should have also been a B over here. And honestly, I would have probably done something, I wouldn't have tried this. It's just not convenient. You have way too many variables. It's going to make it bog it down. No, this is nice and convenient because I get a whole bunch of zeros. It makes anything like the distance formula, slope formula, a whole lot easier to calculate because I'll get stuff to cancel out or get zeros. Alright, so let's just try this. Example 3. Place these shapes in a convenient location. Right isosceles triangle with leg lengths of B, and scalene triangle with length on one side. Sorry, with one side length of A. Yeah, I messed that up a little bit. Alright, so right isosceles triangle. First of all, to get a convenient right angle, I'll probably be using this right here. So I'll probably make my triangle along the y, the x, and then connecting the two. But I also want it to be isosceles, which means I want to go the same length along this axis as I want it to go along this axis. So, and I want the leg lengths to be b. So I'm going to make this point over here be b comma 0, and this point up here be 0 comma b. And there I go. It's convenient. Look, 4 of my 6 coordinates are 0. It's nice and convenient. Stuff will be canceling out a whole bunch. Distance formula will be easy. I can actually do stuff and get a reasonable answer. Alright, a scalene triangle, however, is not as nice as a right triangle. A right triangle, you almost always use the axis like this because this here is guaranteed to be a right angle. Plus, you get a whole bunch of zeros. A scalene triangle, I probably will still use the origin, and if I'm looking for one side length of A, I'll probably make that the base. So if I look here, I chose 0, 0, and then A, 0 here. And the reason I chose it this way is because this is guaranteed to be a length of A down here. It moves A to the right. And it's scalene because I don't know if it's a right angle. It could be. B could be 0. C could be 0. And it could be a right angle. However, it's just a scalene triangle. This covers every single possible case. Alright, now that we know how to place a convenient triangle for our proof, a coordinate proof has 4 basic steps. The first one is to place the shape in a convenient location. Sometimes they'll give you coordinates like I do in the next problem, sometimes they don't. Then after that, you find all coordinates necessary. Sometimes instead of using A or B or C, you'd be using like 2A or 2B or 2C. And that's just because sometimes it's better to have double because you'll be taking half from the midpoint formula. Then after you've placed the location and you find all coordinates necessary, you're going to use the distance, slope, or midpoint formula. And then you're basically going to make a statement that what the distance, slope, midpoint formula has shown. So what was the whole point of doing the distance formula, the slope formula? So for instance, what if I asked you to, given these 3 points, prove that triangle ABC is isosceles? Well, I was nice to you. I already gave you the 3 points. And what I want you to do is prove that the triangle is isosceles. So the first thing I'm going to do is, well, this is best as a coordinate proof. Otherwise, I'm going to be doing a lot of steps in a 2 column. So the first thing, draw my shape. 0, 0, 2p, 0, and p, q. That's what they gave me. The next thing, if it's isosceles, isosceles means 2 side lengths have to be congruent, or they have to be the same length. If I'm trying to prove that this is isosceles, and I'm given coordinates, why don't I use the distance formula? So, quickly plug in the distance formula for segment AB, segment BC, and segment AC. If you plugged it into the distance formula correctly, this is what you should have got. Remember, distance formula is the square root of x2 minus x1 plus y2 minus y1. So if I look here, this is x2, y2, x1, y1. So when I did this, p minus 0, I did x2 minus x1, p minus 0. And when I did y2 minus y1, I did q minus 0. And that's how I got these. P minus 0 is p. P squared is p squared. I can't simplify this any further. The square root of p squared plus q squared is not p plus q. There's way too much in there. I can't separate them and make it nice and easy for me. After I did this segment, I did length of segment BC, plugged in the distance formula, and I was not surprised again to find that I got square root of p squared plus q squared. And I noticed these are the exact same length. That's what I was looking for. However, I'm trying to prove it's isosceles, so I'm just going to make sure it's not equilateral. Segment AC is horizontal, and because the y-coordinates are both 0, I know that segment AC is just a subtraction of the x-coordinates, 2p minus 0. So 2p minus 0 is 2p. This length is different than this length and this length. But I do have segment AB and segment BC being congruent. Therefore, because length of segment AB is equal to length of segment BC, triangle ABC has to be isosceles. And I could say, by definition of isosceles triangle, 2 of its sides match up. But these are the new ideals for today. You should be able to tell me what a midsegment is and how it relates in a triangle. That it's half the length of the third side and it's also parallel to the third side. And you should also be able to make a relatively easy coordinate proof. Make sure you know your length and distance and slope formulas. Otherwise, this section is a lot of review once we get to the coordinate proof. Till next time.